So, derivatives of inverses. Well, if f is differentiable at every point of an interval I, and dy by dx is never 0 on that interval I, then f has an inverse, and that inverse, f negative 1, is differentiable at every point in the interval. And it's important that we say this thing about the interval, and so on, because with sine and cosine functions, we'll see there's a little addition to that or whatever. Right? So, and we just went over general properties of inverses. This, what's highlighted here, might not make a lot of sense. So a translation, what does this mean? This means that we can find the derivative of an inverse function as long as the derivative of the original function does not equal 0 on a given interval. We also know that an inverse function will undo a function. In other words, this is what we were just establishing as our warm-up, right? If you put the inverse function inside the original function, you get x coming out of it. Know this. Why? Because I want you to, right now, together, we're going to apply the chain rule to this equation here and solve for the derivative of any inverse function. Okay? So applying the chain rule. Let's use a color system just so you can follow this. So I'm going to say f of, that's my outside function, the inverse of the function. Now, if I take the d by dx operator, right, I do the derivative kind of thing with respect to x. What are we going to get here? The derivative of the outside? It's very abstract right now. We don't have an actual function like x plus 2 or something like that. What would we call it? We'd take the derivative of the outside, so f prime. You'd leave the inside alone, right? I'm going to use the f prime notation. So we've done the derivative of the outside. Chain rule, what's the next thing you do? Inside, yeah. Times, then the derivative. Now this is tricky with this f negative 1 on here. I already made a mistake with my prime. So I'm going to put it in a bracket. The derivative of this function. But I'm putting a tick mark around the brackets just so you can see. It would get confusing with minus 1 prime. Yeah.
Would you be able to put minus 1 prime or you can grab it?
Do it this way. This is the way you'll see it everywhere else. What about the right-hand side? Equals 0, or I mean equals x. The derivative is 1, right? Now, we're going to solve for the derivative of the inverse. So that means just to isolate for this part of it only, right? I'm going to divide this portion up underneath the 1, right? So the formula we want is f negative 1, the inverse of the function. Its derivative is equal to 1 divided by the derivative with the inverse inside. Now the reason why I show you that is because by the time you get to the end of this course, you don't want to memorize a ton of formulas. If you use this often enough, you'll know it, but it comes up, and I'll guarantee, pretty close to a guarantee, you'll see something that will require you know this. However, I don't have this memorized so much as I just take a second here and I think I know what an inverse is, and I think of this. And I just, oh yeah, and I just kind of work it out. I do it in my head. I don't actually literally write it out anymore, but I used to write it out. And it takes, after you've done this a few times, it takes maybe 10 seconds and you just say, yep, this is the formula. It's really just apply the chain rule, isolate. Okay? Now, so this is what we were after here, that's what we just wrote out. But that's where it comes from. Knowing what an inverse is and just doing the derivative of the inverse. So there's that statement. If the derivative of x doesn't equal 0 for anything, any value on the real numbers, then the inverse is also differentiable. Okay? Now, as I mentioned, if you truly understand what an inverse is, you can always work that formula out, and this is how you work it out. I don't advise you to memorize it. It'll be one of those things where you work it out a couple times. Maybe you use it often enough it kind of becomes second nature for the next 2 weeks. But then in 2 months, you might be like, oh, what? Work it out from first principles. It'll take you a minute the first time, 10 seconds after a couple times. You might even just know. Okay? Now, I want to see something here. This formula, in a case like this, doesn't actually save you a lot of time. But you have to understand this because later on, there's things where you just can't get around using it. So, find the derivative of the inverse of this expression here. Using the formula, it's going to be longer in this case. I'll show you what I mean after. But using this formula. Maybe I'll change my color just so that I can use greens and blues. The formula that we just came up with right here, okay? Well, we need a couple things here. In order to do it this way, I'm going to just do an aside over here. Actually, like I said, it's quicker the other way, this case. What is the inverse of this expression here? Well, if f of x is equal to root x minus 3, how do you find the inverse of that expression? Well, y is reversed, we'll call f of x y. So we're going to reverse with the x. So, how would you undo the square root? Square it. So then you've got x squared plus 3 is equal to the inverse. I'm going to call it the inverse here using this notation. Okay? Right now I could do, now I got my left rights reversed, but I want you to see how the formula works. Oh, what if I did the derivative of this expression here? You can tell me what the inverse's derivative is? It's 2x, right? Got me on that? Kind of? Question. You know what? I forgot one little detail though. Absolute values and stuff like this. I'll leave it out for right now, but do you realize when you take the square root of something, like this inside here has to be positive, right? You can't have negatives in there. Does that make sense? So this would actually have to be a positive, and then you take it out and so on. But I'm not going to work through that too much, okay? But there is absolute values involved here. This is just, that isn't what I want to focus on, but there actually is absolute values. So, to do this formula way then, we've already got the answer, it should be 2x, but according to this formula, you need to find what the derivative is when you put the inverse inside the function, right? You follow that? That notation, like I said, this is not easy this way. So, I'm getting blank stares. Yay or nay? I'm going to say, how does this formula work? Even though we have the answer that we want here, right? I don't know, I'm kind of waiting to see if you guys, yeah? No? X squared plus 3 plugged inside, right? Yeah. So, Maybe we'll talk about this first. What's the derivative of f? F prime of x. I hope you recognize that's the power of a half, the square root, right? So I'm going to say it's 1/2 x minus 3 to the negative 1/2. The derivative of the inside is 1, the x minus 3 part, so I'm not going to do anything. So this means, what is this expression then when you put the inverse inside it? We know what the inverse is. We're saying it's this, minus the absolute value portions I've talked about. But x squared plus 3 put inside there. Let's see what that is. Negative 1 of x is equal to 1/2 x squared. We put that in for the x here, right? It's confusing because you put an x in, an x squared kind of expression in for the x. X squared plus 3. 3. Now, you guys can see how it simplifies 3 minus 3, right? Inside. What am I figuring out? I'm figuring out this portion of the expression. So then what? You get x squared in there with the negative 1/2 around it. You got to remember what negative 1/2 means. So just a second here, which is equal to 1/2 x squared to the negative 1/2. Hey, we know a bit about what happens with exponents on exponents, right? What do you do to them? You just multiply them, right? 2 times negative 1/2 is negative 1. Okay? Nobody's shouting stuff out, so I'm just going to put this here. What does this turn into? 2x. Okay? Now, see what the formula was? Now I've just figured out what the denominator of that formula is, right? Like I said, this formula way in this particular case is lengthy. It's not going to save you any time. But I want you to just see how this kind of works. F negative 1. I'll use weird. Derivative of the inverse according to the formula is equal to 1 over 2x, and we should get the same answer that it was before. And is this the same as the other one? Yes, you flip the reciprocal of the, yeah, okay. The reciprocal of what you're dividing by. So 2x. It is the same as this. Now, I just wanted you to see what each part means. You have to figure out the derivative with the inverse plugged inside it. Now, we'll be using charts sometimes. We'll be using like chart data and stuff like that. You won't actually be working it out like this. And I told you this, by far, if you're given information like this, you do it this way. But thought we'd try this one just so you can see how the parts fit together. So don't think you're going to be doing all of that all the time. Now, another bit of trig review. We already talked a little bit about this. Things you need to remember about trig functions, and we've talked about it before. Unit circle. Radius 1. I don't ever advise you to memorize the unit circle as in, you know, the coordinates all the way around. All you need to know is 2 triangles and just fit them in where you need them. 1, 2, radical 3, 1, 1, radical 2. But to understand the unit circle, the idea is that it has a radius of 1, and the coordinates are related by the Pythagorean theorem. meaning this triangle here, c squared is equal to a squared plus b squared, right? And we know that the c is 1, so 1 squared is equal to the y side and the x side squared, right? That's how they're all related. But show how you can express every x and y coordinate in terms of sine and cosine functions. You guys remember this? So this here, what I'm saying is that x comma y on the unit circle, you guys remember? If you don't, and I think I just heard it, so I'll do this one for pi 6 here though. But for any of them, what do we say here if the angle is theta? The y coordinate, wasn't it opposite over hypotenuse of 1, right? What's opposite over hypotenuse? Sine. And then the x coordinate is the adjacent side over the hypotenuse of 1. That's going to be the cosine. Now this shouldn't be news to you, it should be reviewed. This is the same as saying the cosine of theta, the sine of theta. And this comes in all the time. Okay. This is where the Pythagorean identity comes from. Cos squared plus sine squared is equal to 1, right? And then all the variation, the other two variations from that. You guys follow what I'm saying there? The cos, like you know the formula, but if the x squared plus the y squared equals 1, it should make sense then that the, well, instead of x, you could have the sine, or cosine of theta, and then the sine of theta squared, right? Added together equals 1 as well. That's the Pythagorean theorem. That's where it comes from. Now, do have 1, 1 radical 2 and 1, 2 radical 3 memorized, because then you can do the sine or cosine of, or tangent of any of these, right? Meaning, give me an angle from one of these sides here. Don't give me from the first quadrant. Somebody. And don't give me one right on a 90 or whatever, 270 or something.
7 by 6.
Okay, 7 pi, oh, that one. Okay. Yeah, so 7 pi out of 6. So as soon as this, I think, well, the reference angle, you know, it's a pi sixths over 180, like just past 180, past pi radians, okay? So here's pi out of 6. And that's really fuzzy, but that's pi out of 6 in there. That's the reference angle I'm using. What is the small side of the triangle? It's 1, but it's going down, correct? So then we'd say negative 1. This is 2, and it's just a 2. And to the left, so it's negative root 3. Now, if we said find the, I don't know, sine, cosine, tangent, which one? Sine. The sine of 7 pi out of 6. You're going to look over here. You're going to say, what is the pi out of 6? You're using this triangle, right? Opposite over hypotenuse is negative 1/2, right? Okay. I would not spend any time memorizing the triangle, but you got to be able to fit reference triangles. Is that, you guys use reference triangles like that? You didn't memorize, well, you can memorize it, I'm saying, but it's a waste of time because you'll forget it in a week. But you do need to memorize 1, 1 radical 2 and 1, 2 radical 3 for the 30/60 or pi 6, pi thirds. Pi quarters is 45 degrees, right? Okay. Now the graphs of sine and cosine. We've mentioned this before here, but I'll go from 0 to 1, negative 1. You do need these memorized because it's just a quick way to reference what some values are. So if in the center we've got pi here, what does the sign look like? A sideways letter? S for sine. Yeah. Goes up to here, I'm putting my 1 way over. Down to negative 1. Okay. I don't have enough curviness on my second half of that, but whatever. You get the idea. Then you can see. Where is sine positive? Sine is going to be positive here and here at the same spots, right? Like this is 0 to pi halves, or 0 to 90. Sine is positive between 90 and 180, or pi halves to pi, right? And then negative for the rest of the CAST rule, you guys know? That's another way of thinking. Okay. Likewise with the cosine function. Here's my pi here. Lessons. Scared someone, eh? Pi halves, 3 halves, okay. Okay, that's a freehand graph. It's rough. I didn't quite hit my 0 perfectly right here, but you get the idea. You should be able to rattle one of those off real quick. Anyways, for the cosine function. The one people forget, because you don't do a lot of it, I know in pre-calc 20 and 30, you don't look at the tangent graph much at all. You don't manipulate it. But just think about it. Tangent is what divided by what? Sine divided by cosine. By the way, the tangent function is also, because it's sine divided by cosine, it's the slope of this, right? Because y is the sine, and the cosine is the x, right? And the slope of this line, y over x, right? So where's the tangent? 0. The slope of this line is 0 here. It's undefined here at 90 degrees, or pi halves. It's at pi, it's going to be 0 as well. It's a horizontal line. And then in between, you got positive values. You got negative values at 3/4 pi. Stuff like that. And likewise, negative over here at 7/4 pi. So when you graph this, it's going to look something like this. And just think, you can't divide by 0, right? It's sine over cos. You follow this, right? So the initial value at 0 is 0 divided by 1. So it starts at 0. If I call this, how many squares did I use? 1, 2, 3. Okay. And then I can't divide by pi halves. So 1, 2, 3. I'm going to put a asymptote here. And then 1, 2, 3. Another 0. 1, 2, 3. Asymptote. And then so on. Okay. What does it look like? Do you guys vaguely recall what this graph looked like? You guys didn't do much with it? No? Okay. Fair enough. So, what you're going to do is you're going to go through. It's going to hit 1 at, where did I put? Yeah, I used spaces of 2 here. At pi quarters, it hits 1. There. It's going to be negative 1 here. This is 0. So I'm going to go there and there. These are the only careful points you have to plot. Okay. It's going to come out from negative infinity. And so on. This should be right there. But just pull it down because I can't attach to the other one. Anyways. That's what a graph of the tangent function looks like. It's too bad because the old courses, the ABC 30, we used to play around with tangent functions too. But it's not a big deal. You're not going to have to graph this, but just keep this in mind. Because you're dividing by the cosine function, you have asymptotes there, values where tangent is not defined. Okay? And it's the slope of the unit circle. There's another way of thinking of it, too. All of that jazz. And then what? Now to apply this now to calculus. So far we haven't done any calculus. Working out the derivatives of inverse trig functions. The trig functions are not one-to-one, so they don't truly have inverse functions, but we can overcome this by restricting their domains. Find the derivative of an inverse, y equals sine of x. We need an interval. We need to think about an interval where the sine of x is never 0. Now, as I said before, previous page, the sine looks like this. It's 0 here, though. That's find the derivative. We need an interval where the derivative. Oh, my mistake. The derivative. I knew it as I said it. So we need to stop there, right? You know how this would go backwards? We need to stop there. What are those two values? That's from negative pi halves to positive pi halves. That's where you get 0 for the derivative. So we're only thinking between these two values. Okay, so this is my negative pi halves. This is what I meant by this. For this argument, to create this derivative, that's what we're talking about, that portion of the graph. Now, on this interval, we're going to find the inverse derivative of that inverse function. Now, we've talked about what an inverse is, and we kind of know what this function would say, what is the angle that gives me an x value of? So we're going to rearrange and use implicit differentiation to solve this. And honestly, you're going to have some formulas, but I would never advise you to remember the trig formulas, because you can work them out from first principles rather quickly after a little bit of practice. So I'm going to use a different color. Okay. To rearrange this one, sine negative 1 of x. It's the inverse. Really, another way of saying that is x equals the sine of y. You guys agree with that? So, that'd be like saying the sine of pi 6. Isn't that what we did? Is equal to 1/2? Oh, we did pi thirds. Whatever, the same argument. Okay, on the other board. To rewrite this same information, this is the same as saying the sine negative 1 of 1/2. One of the possible answers is pi 6, right? That's what the inverse means. So, what we just did was go in the reverse order, right? We're rewriting this kind of information in this form, okay? You guys follow what we just did there? We rewrote the backwards way. Then I said use implicit differentiation. So we're going to take the d by dx of each side. I'll even actually show that this time. Of the x expression is equal to d by dx. Take the derivative with respect to x. With respect. Okay. I think the left side you guys got down. Hope so. It is 1. Okay, great. And the right side, I think you got it down. Derivative of the sine function, cosine function. Of y, though. And you say, wait a minute, there's a mismatch, right? We're doing it with respect to x, not with respect to y, so we have to add in dy by dx. Let me put that in brackets just kind of isolate it, right? So we got dy by dx. I'm isolated for dy by dx, it's 1 over the cosine. The cosine of y. This doesn't get us too far. Use the Pythagorean identity. Huh? Why would I use the Pythagorean identity? I'll tell you a little bit why. I'm going to just put this down. And I'll do it like this. The cos squared of theta plus the sine squared of theta equals 1. If I was to isolate this expression just for the cosine, I'll move it up because I could do that. Oh no, I'll keep it there. I'll just write that down. Well, then that means the cosine of theta is equal to 1 minus the sine squared under a root sign. Okay? Does that make some sense? Now, it might not make sense why I'm doing this, but just because I told you to use the Pythagorean identity. Okay? So dy by dx, I'm subbing this in, is equal to 1 over, and instead of cosine of y, I'm going to use this form of the identity, right? So put it under as a root. And say, this is more complicated than the previous expression, right? It is. This sucks, and it does, you think. You're going to love it, though. What did we say right at the start of this whole thing? What is the sine of y equal to? I said it's equal to x, right? Because I said then use your knowledge of inverses to find an expression in terms of x. Does it make sense and we knew from the start x, oh, that's not going to work, x is equal to the sine of y. So we're subbing in again. And that becomes 1 minus x squared under the root sign. What did we just do the derivative of? What was our starting expression? Y equals sine negative 1, the inverse of the sine function. Now I showed you how to work this out, and they can all be worked out in a similar fashion. We're not going to work them all out, but the kind of stuff that we did there. So, the bottom line from this is that the derivative of the inverse of sine, arc sine, whatever you want to call it, is equal to 1 over. And you can use this formula as a shortcut. It isn't that hard to memorize, I guess, but like I say, towards the end of the year, you'll have too many things to memorize. And once you work this out a couple times, it's like, okay, I get it. I know the argument. I don't have to memorize this formula because there's too much in my brain. If you do understand the inverses. But I have a summary and I have the formulas on the next chapter test you have. You'll have this formula, the 1 over root, and all of these. Now right now, don't worry about the fact that there's u's in here instead of x's. We'll see more. This is u prime, which really means du by dx. We'll see more about that later, okay? That's just, okay, so this is your summary. All of those formulas are given here for the cosines, the inverse of tangent, etc., and the cosecants and stuff like that there. Now, you might be thinking like, This is crazy. But we'll do it one of two ways. Or we'll do it two ways here. Can we do this the formula way? Can we do this the other way? So I said show two ways in this example, and in this example only. Because, like I say, later on, in a couple months, you might not have this formula memorized. You should be able to do it from first principles, and you'll see. Now, this formula here, this is where you have the arcsine of u. And u is if you have anything other than x, right? Like in this case, 8x squared. That's your u. It's your, remember how we said with the chain rule, we could say du by dx? It's the thing inside, okay? So the formula way, with the chain rule basically applied to it, that's what this is. So according to this, the derivative dy by dx, let's apply this formula. Well, what's the u prime? The u is the inside, right? What's inside there? 8x squared, right? So what's the u prime? What we're going to put on here? We're going to have 16x, yeah. So 16x. That's the top. And then the bottom, 1 minus whatever the u expression is, squared under a root sign. 1 minus 64x to the 4. Oh, I'm doubling up on the root sign here. That's no good. So it's easy to use that formula, relatively. Right? You can just do it in one step. What if I said show two ways, and I did. And then you're thinking like, oh my goodness, it actually isn't that much work. So, if we were to do this from first principles without the formula, that's what I'm going to show here. So, or, to rewrite that without the arc sign, without the inverse of sine. What's that same information? Thing. This is what I'm asking you. So if I'm giving you an expression like this, except that's way too big, how can I rewrite it like this without the inverse? Ah, okay, you're catching it. So this is the same information as what? Almost 8x squared, though, we'll say. The answer is 8x squared, right? Which equals the sine of y. Then you could pull off the derivative of both sides. So I'm going to just scratch that in here. I'm not going to actually write it. So d by dx on this side, d by dx on this side, right? What's the derivative of the left side? The 16x, right? Which is equal to, well, what's the derivative of sine? It's cosine. Cosine, y, then dy by dx. Okay? And then you think, what the devil? What do we know from the Pythagorean theorem? Whenever you do this, you got to have the Pythagorean theorem in your head. It's the square root of 1 minus sine squared, right? Okay. So 16. I guess I'll first isolate. My mistake here. I'll maybe isolate for dy by dx. depending on what your problem is, this might be enough, and you wouldn't even go any further if you could substitute something in. But we will assume maybe we don't. So, we know that 1 minus sine squared under a root sign is the same expression. We worked that out before. Now there's a reason why I did that. Because we know what the sine of y is, right? 8x squared. So if we square that, put it underneath here, we get the same answer as before. dy by dx is equal to 16x all over 1 minus under a root sign 64x to the 4 when we plug in 8x squared. Where am I getting 8x squared from? I'm getting it from here, so I'm plugging in for here. So then, where was I? 64 x to the 4. All I'm trying to show you is that if you remember the formula correctly, you're great. If in a few months you forget the formula, but you know the Pythagorean theorem and so on, you're not hooped. You could still do this. You're good, right? Now, there's 4 minutes left. I want you to try the problem number 1 anyways, and maybe 5. I think that's what I have down here. Oh, I don't have it here. Okay, it's on the next page, but I knew I wasn't going to attempt to try to get through this. I think number 1, page 175. You guys were very patient and kind to me. But do number 1 for sure. Yeah, and 5. And use the formulas to do those ones, okay? What formulas? Which formulas, I mean? These formulas, right? Start on 1 and 5 and see. I'm thinking in the 4 minutes you should at least get 1 done, 5 done, maybe 6. The answers are in the textbook, the answer book with the front 2 for the evens. Oh, I have them down there too, okay. Okay, so get a start on it. Tomorrow we'll look at some more. I'll stop the recording and then answer your question.